to thank everyone for coming tonight. We've got a lot of good information we're going to hear tonight, so thought it would be best to have us all here together so we can hear the same information. We are. Before I go further, I want to note that we do officially have a quorum for each MUD. So on behalf of, and I'll just name them, the Woodlands Metro Center MUD, the Woodlands MUD 1, Montgomery County MUD 6, 7, 36, 39, 46, 47, 60, and 67. I call the meeting to order. So simultaneously, all those meetings are officially open. The second item on the agenda is to have public comment, if there is any. I don't see any folks from the public other than directors, but I'll at least bring that up. All right. So before we have the engineers come on, I just want to note a couple things. First off, we are recording it tonight. So we've got a recording of the presentation. We do have two. So in order for the recording to fully pick up all the audio, it needs a mic. So there's a couple mics. The speaker tonight will have, speakers will have a lapel mic. And then when we get to the Q&A area, we'll be passing around a mic to those that have questions. So if you have a question, which I'll explain here in a minute as well, we'll get to that and we'll pass the mic around. Let's see. In order to just basically stay on track, and I think something that's been done in the past worked fairly well, is if you have a question at a particular time, I would say raise your hand, and the engineers are going to identify who you are and jot you down. And then once we get to the question portion, we'll just go right down the list of who raised their hand in order and go through, and you can ask your question. And at that time, it'll be a lot easier for us to start moving the mic around person to person to person to get all the questions asked and answered. So I think with that, that's all I had. So I'll pass it over to Mira.
Thank you.
And you're welcome.
Thank you so much for being here tonight to talk about the wastewater treatment facility number 1. Can you guys hear me? No?
Yes.
All right, I'm going to try to scream as much as I can, but if you can't hear me at any point, if my voice goes lower, please give me a thumbs up so I can try to increase my voice. But again, thank you for being here tonight. Really appreciate giving us the opportunity to present where we are today on this project and study, the wastewater treatment plant number 1 condition assessment. Before I get into the presentation, I wanted to introduce our team here that's with me today. A little bit about Carollo Engineers. Carollo Engineers is a water-only firm. We have been doing water, wastewater, stormwater, anything to do with water for over 93 years across the country, as well as Canada. So we are a North American firm only. With me, I have Queasy Dose. Queasy is our chief structural engineer for Carollo Engineers. He was also the structural lead for this project. Alicia James is our asset management lead on this project. And nationally, she's one of our leaders in asset management and condition assessment. So she may not speak a whole lot today, but she's also going to be acting as a moderator. So when you raise your hand, please don't mind Felicia coming to you and jotting down your names if she can't speak from there. And my name is Mira Victor. I think I've met a few of you before. I am Senior Vice President with our company. I also lead and manage the Texas region for Carollo, and I am the lead on this project. With us, we also have Stephen Foster with WJE. They specifically perform structural assessments. So I'll let Stephen talk a little bit about WJE.
Yeah, thank you, Mira. Like Mira said, I'm Stephen Foster with WJE, and our firm specializes in condition assessments and evaluation of existing structures. My expertise is in concrete infrastructure projects, so water, wastewater. I worked a lot in every major city in Texas and other states throughout the country. I also specialize in corrosion assessments, specifically in those environments, and concrete structures in particular. So yeah, grateful to be here and happy to answer any questions as they come up.
Thank you, Stephen. So at Corolla, we have done similar projects throughout, not only in Texas, but throughout the country. We have completed about over 500 such studies nationally and over 100 studies in Texas particularly. In fact, we have about 7 going on currently just in the Houston area. With that, we'll talk about the agenda, what we're going to talk through today. I'll start and give you guys an overview on the project schedule, where we stand today. Talk through the condition assessment, the verification process that was part of our scope of work. And then talk about the existing plan capacity evaluation. What the capacity of the existing plant is in terms of the process units, how much water can they treat? And finally, talk through the next steps. So project schedule. I know you guys have seen this before, and this has changed a little bit over time, just because the data that was coming in and when we needed additional studies done. So for example, the condition assessment review, we are targeting, it's almost 90% complete. We are drafting our report based on the comments that we get from here today, and we'll get that to you by the end of the month. The criteria, we've already completed that. We are also progressing on our alternative evaluation process. We are going through the costing of the alternatives and evaluating each of the alternatives based on the criteria we had developed for this project. And finally, we'll come back next month and show that evaluation to you all, where we each of the alternatives stand against each of the criteria, including the cost. At the end, the final discussion item is the project delivery analysis, where we are going to evaluate whether the project, whichever alternative gets selected, how that should be implemented, whether you do a CSP process or a CMAR, construction manager at risk process. So let's talk through the existing condition verification update. The next 2 slides are going to be a recap of some of the information that was already presented at the trustees meeting. Our scope included verifying the previous assessment that was performed by another consultant, reviewing and updating the condition data that was developed before, because that assessment was done in 21-22 timeframe. So we wanted to update what the condition of all the assets at the treatment plant were. We also wanted to calculate the remaining useful life of each of the assets. And then based on the assessment, come up with a list of repair in place components for each of the assets at the treatment plant that would form the basis of our base case, alternative 1. While we do that, we also were tasked to perform a regulatory compliance and deficiency to make sure that the existing plant can meet the TCQ criteria, which is based not only on the process capacity of each of the processes units at the treatment plant, but also the hydraulic capacity of the plant. So we did perform that evaluation report. Our approach to the verification process, the condition assessment, was we did a 1-day visit at the site back in October. We assessed 324 total assets at the site, and you can see a breakdown of all the assets types: 108 mechanical and process assets, 59 structural assets, and 157 electrical and INC assets. The objectives of our assessment was to make sure, as I said earlier, to update the results from the prior study that was developed by another consultant, update the remaining useful life, and then identify the repair in place alternatives. Last time we showed you guys the mechanical and electrical and INC asset notification. This time around, we have added structural, because as you are aware, last time, based on our assessment and the leaks that the staff were seeing at the existing structures, we wanted to do a more in-depth assessment of the structural assets because that is the main majority of the cost increases that happen is based on the structural assets. So we wanted to make sure we get thorough data back from the structural asset assessments, which is what we performed, and Stephen and Preeti will talk through that. Based on our assessment, we identified these 5 structures that to perform the in-depth assessment of the structures. Again, this was based on this list was based on the condition of the asset, when the asset was implemented or constructed at the site, if visually we could see any challenges at the structure, whether it's cracking, leaks observed by the staff. And based on all that information, we came up with 5 structures to perform the structural assessment on. And the reason we couldn't do every single structure is because of the cost, right? We didn't want to be cost prohibitive. So we tried to target some 5 structures that we could potentially make sure we carry forward the same assessment for all this, assume that for the same assessment for all the structures. So with that, I'm going to give it to Queasy to talk through the structural assessment part.
Thank you, Mira. Hopefully everybody can hear me also in the back. If not, just give me a thumbs down and I'll try to kick up my voice a little bit. Okay. So on behalf of Corolla, we initially came out and we visually looked at all the structures on site. And we performed a visual analysis, looking at it, touching it, feeling it. But after doing that, we realized that we had to go into a more in-depth assessment of the various structures. And so we brought on WJE, Mr. Stephen Foster and his group to be able to help us to do that. On the screen are the various structures that we assessed. So for the visual assessment, we selected digester number 4, chlorine contact basin number 3, and you can see digester number 4 and chlorine contact basin. The digester is right in the middle of the plant, and the chlorine contact basin is to the south or bottom of the page. We also selected 3 structures further to do a more in-depth analysis, non-destructive testing and laboratory testing. And I'll get into that in the next slides, what those entailed. We picked 3 structures: the aeration basin number 3, top of the page, the clarifier number 2, middle of the page, and then lift station number 2 to the left of the page. Why did we select these 5 structures? When we did our structural analysis by just visually looking at all these structures, these were structures that represented the rest of the structures on site to the best degree as possible. Based on the age of the structures, the average age of the structures are about 40 years old. And so they represented a large amount of the structures there on site. On the structural observation too, when we looked at each structure, we looked at how many cracks there were in there, how much deterioration was going on. And these 5 structures were representative of the condition on site. Additionally, though, we also had some field reports. We had some existing drawings that we could go back to, look at those existing drawings and verify those conditions during testing. And these structures had existing drawings to be able to help us to do just that. But more also importantly, we want the plant also to be in operation at the time we're doing the assessment. We can't simply just shut down the plant. That would not be good. And so we wanted to make sure that we selected structures also that will work with the plant as well. Then we also talked to the plant staff to get information on some of the conditions that they've experienced over the lifetime of the structures, because that will also help us do a better assessment based on some repair work they've done in the past, based on the observation on leaks. And so that will help us also determine what to do. As you probably note on the screen, some of these structures are rectangular, some are square, some are circular. We did a decent job of trying to mimic the conditions of each structure assessed. So for example, the clarifiers are circular, so we needed to pick a circular structure to assess. The aeration basins are more rectangular but bigger. We want something on a bigger scale to assess. And then the digester number 4, something a little bit smaller or medium size, we wanted to pick that also as well to assess. And the lift station and chlorine contact basin also are unique structures that represent what is going on site. So let's talk about the visual assessment methods. What is visual observation? Visual observation from a structural engineer standpoint is basically looking at the structure, looking at it with the eye, touching it, feeling it, maybe knocking it with a hammer, just to make sure it is still sound from a structural standpoint. And so that's what we did. And WJE further did that on those two structures that we identified for visual assessment. Why is that important? Because just by looking at the structure, we are able to identify areas of concern. Is there rebar reinforcing corroding? Is the concrete kind of breaking apart? Do we see the crack pattern that is occurring that tells us something about the structure that perhaps will help us assess it even further? And so based on that, we also did hammer sounding. So we basically take a hammer and we hit the structure, knock it around. And perhaps if you can think about something solid, when you knock it, you get a distinct sound. But if there's a void behind it or if it's hollow, the sound will also show up. And so you're able to detect those two different sound conditions, and you can tell whether a structure is sound or if there's a void behind it, maybe indicating that some corrosion is taking place behind what you can see, or perhaps during the pour process, there was a void there due to maybe segregation of the aggregates because they were not maybe compacted well enough. And so there's a hole behind it. And so that hammer sounding is important to do that. It helps us identify areas of corrosion and then voicing the structure as noted. Let's get to non-destructive testing methods. As the topic indicates, it's non-destructive. We don't want to do anything that will bring damage to the structure. And so it's called non-destructive. So all these testing methods result in no damage to the structure. It leaves the structure as is, as we saw it, that way it can continue to function. The various test methods that you see there, the half-cell corrosion, electrical surface, linear polarization, and ground penetrating radar, these are what I'll call equipment-based readings. So pretty much it's an equipment that you either put to the face of the concrete or you connect to the reinforcing by drilling a small hole and attaching a cable to get to the reinforcing, or it's an equipment, depending on it, you connect to both the concrete and the steel to get a reading. And so that is what all these four tests give us. So it's a handheld device and equipment connected to these things to be able to get the reading. What are the purpose of it and why do we want to do it? For the half-cell corrosion potential, for example, it helps us identify, is there active corrosion taking place? So we'll get a reading. And from that reading, we're able to interpret whether there's some active corrosion taking place behind the concrete that we cannot see. Electrical surface resistivity, it also determines the risk of corrosion. What are some things that are taking place behind when we put the equipment there to give us that data, and we're able to read that. Linear polarization determines the rate of corrosion. How fast is this thing corroding? And that equipment is also able to give us that data. And then finally, ground penetrating radar is also another equipment that we put to the face of the concrete structure. And with that, we're able to determine what is the size of the reinforcing in that structure. This is very helpful because we can go back to the drawings that we have and compare to see, are they the same or is something changing in the in-place field condition? It also tells us not only the size of the reinforcing to estimate that, but it also helps us to estimate the spacing of the reinforcing, because that's very important to the structural integrity of a structure. And so that equipment will help us identify just that. And then finally, it identifies the embedded reinforcing and also the cover depth. Now, the cover depth is the face of the reinforcing to the face of the concrete. So that's the cover. Typically, we want to see a minimum of 2 inches on structures such as this in a water wastewater environment, because you want to protect the steel, so you need enough concrete to do that. And we'll get into that in some of the testing methods. And so the penetrating radar will help us estimate this cover embedment depth when we use that equipment. Let's get to the laboratory testing. So whilst we can do this, the earlier one, which is using equipment, there's still stuff that we generally cannot see. And that we have to go into the lab to do some more in-depth study. And so for the structures, we took cores. Basically, we drill a core sample, which is a 4-inch diameter by 8-inch long sample from the structure, concrete piece. So we extract that out, and then we test it in the lab. Now, there are various tests that we do on these cores. For all the structures that we did a total of about 26 cores to test them, because we wanted enough data to be able to come up with a great assessment of what we are actually seeing. What are some of the tests that we did on these cores? Let's start first with carbonation testing. When we think about air, air is made up of different components, and carbon dioxide is one of them. And as humans, we don't inhale carbon dioxide, and it's also not good to some extent for the concrete. Here is what happens. When carbon dioxide comes in touch with the concrete, it actually begins to work against the chemical properties in the cement. So there are hydroxides. These are some chemicals in the cement. and it breaks it down. The cement is typically alkaline. Opposite of alkaline is acidic, so it's not acidic. But the carbon dioxide reacts with it, breaks it down, and gets the concrete to go in an acidic direction. That is really not good for the reinforcing in the structure. So now it begins to deteriorate the concrete and then begins to deteriorate the reinforcing with the right amount of water and oxygen when they come in contact with it. So we want to measure that level within the structure. Because we know the concrete cover, we're able to do that. How do we test for the carbonation? Well, when WJE takes it to the lab, basically, they take the core sample and they add a solution called phenolphthalein. So think about a chemical. So that's a chemical. They add it, and depending on the color change, be able to tell the amount of carbonation that has taken place on the concrete core. Another lab test that is done is the chloride ion titration test. Chloride is also another chemical, we can say. So when a concrete mix is usually done, there are several chemicals that are put in it sometimes. We call them admixtures. These help the concrete to be poured either easily or to strengthen the concrete or to make it more durable to last for a longer time. But sometimes, though, some of these chemicals contain chlorides. Why are chlorides so dangerous for a concrete structure? Because when you have the right amount of chlorides in concentration, when you pour the concrete over the reinforcing, the cement paste has a very good barrier that it forms around the reinforcing. That is why it doesn't corrode, because there's a chemical reaction that takes place and it coats the reinforcing, preventing it from corrosion. What happens with chlorides is when you have just the right amount of chlorides in concentration, it will destroy that protective barrier. And then now the moisture and oxygen is able to get in and begin to deteriorate the reinforcing. And so the testing in the lab, it uses various acids and chemicals to test the cores so that we can tell how much chlorides are in the cores, thereby indicating how much chlorides perhaps have affected the structure. You could also have chlorides also in the wastewater stream because this is a wastewater environment. And so despite the fact that the concrete mix itself could have had it, you could also have it in the wastewater stream, and that could also affect the structure. Another lab test we do is petrographic examination. A big name, but really simple. Basically, it's just taking the cores, breaking it up, looking under a microscope to see what the constituents were of the cores, because that tells us a lot about the concrete mix that was used. What type of aggregate was used? What type of sand was used? Did they use any what we call supplementary cement materials like fly ash? We can see that under a microscope. And then more importantly also, there are some cracks that are actually not visible to the naked eye. Do we see that under the microscope? Because eventually those will actually deteriorate the concrete. And so we want to do that with a petrograph examination under a microscope. And then finally, one lab test, which is very important, is also the concrete compressive strength. Concrete is very good in compression. And that is why they act as strong columns, because when you load it, it can take so much. But it's weak in tension. That is why you provide the steel. The load at which the concrete will fail, just before it will fail, is what we call the compressive strength. So you load it up, you take the course, you load it up, and right before it fails, you get that load, and that's the concrete compressive strength testing. For these structures, the existing drawings were available to us, so it was really good. We're able to verify. The minimum on the drawings that we were able to look at was 4,000 pounds per square inch. So compressive strength is measured in pounds per square inch. So you take the course and then you measure that. And then we are going to see what the results show when we tested our course. So compressive testing, we get the compressive strength of concrete, and it tells us overall what the quality of the concrete is, if the structure still has the strength that it needs. So let's go into the in-depth analysis with the structures that we tested. First, we'll start with the chlorine contact basin number 3. The picture on the left shows a lot of widespread deposits and biological staining. This is a wastewater environment, so the water coming in is not clean drinking water. It's water that's going to be treated. And so we see some of that staining effect taking place. Additionally, though, there are some bacteria that thrive in that environment. And so whilst they thrive in there, they produce acids, and these acids attack the concrete because they're trying to break the concrete down. And so we see that widespread erosion of the concrete paste, which is that first surface layer of the concrete, being eaten away by some of these bacteria. Additionally, because the bacteria is so active in this environment, it also begins to now attack not just concrete, but other elements of the structure. So for example, in the chlorine contact basin, we had a concrete masonry unit, CMU wall in there, easily abradable, could easily take a the sharp edge and then scrape it off because it's a very aggressive environment and the bacteria is beginning to eat it up. On one end, though, we also saw an isolated concrete crack, very isolated, 10,000ths of an inch. And so we captured that also in that photo. Then additionally, on one end also, we saw isolated delamination or spalling of the concrete wall. So delamination is usually when the concrete, for example, is not well bonded, and so it begins to spall off or come off. And the spalling also maybe a piece of the concrete may be coming off. It could just have been some mechanical impact, maybe somebody hit it, or perhaps the concrete at that point was probably deteriorated by some other means. So we captured that as well, an isolated incident. We talked about the concrete cover, which is the cover from the face of the reinforcing to the face of the concrete. We want to see 2 inches. Well, fortunately for us, at the chlorine contact basin, there was a point where the reinforcing was visible to the naked eye. So we actually measured it. And you can see the dimension there, 2 inches. So that checks. And then on one end, we have 3.5 inches. So after all our analysis of the chlorine contact basin, what is our recommendation? Well, we recommend periodic visual observation, just like we did, every 3 to 5 years, just to see the structures continue the way they are, or if they deteriorate further and need further action. Non-destructive and lab testing and in-depth study, we suggest every 10 years for that to be performed on the structures. And then areas where the concrete, we see delamination, spalling, as we showed in the previous pictures, some of them with the acid attack and things like that. We are recommending concrete repairs and the application of a coating system to protect the structure and extended longevity of the structure. And we are recommending all these repairs and coating applications to take place within the next 3 to 5 years. So good time to actually do it. And that'll also be the same recommendation for replacing the CME wall, the concrete masonry wall. We are recommending actually replacing that with a concrete wall, since that will give you more durability. And that can also happen during the repair work within the next 3 to 5 years. We'll go to our next structure, digester number 4. In digester number 4, we see the same thing on the left with the biological staining and the widespread staining. This is a wastewater environment, and so not surprising we have that. But we also see paste erosion, usually at the top of the wall, above, just right at the water line, above the water line, because that's a turbulent environment. It's also exposed to moisture and oxygen, and so with the bacteria also, that's where the attack is usually strongest. At the bottom of the walls and to the slab, none of that was observed, which is typical for such structures. In one end of digester number 4, though, we talked about the concrete cover. So there you can see particularly a reinforcing being exposed. Likely the concrete has spalled off or broken off due to some corrosion, something happening there. The reinforcing is too close to the edge, so you don't have that 2 inch, but that's an isolated incident. So we captured that also occurring there. And then as we walked around the structure, we see local vertical cracks, and that's typical, very fine line hair cracks. That's typical because usually with concrete, you have cycles of temperature, cold, hot, all that going on, and that allows the concrete to expand and contract. And so you have these temperature or shrinkage cracks. None of these that we saw were leaking as far as we saw. So what is our recommendation also for digester number 4? Again, the same thing, periodic visual observation every 3 to 5 years, monitor just like we did and see if anything changes. And then we have also recommended non-destructive or lab testing every 10 years to see if the situation deteriorates from the benchmark that we have today. And then for those areas where we have the localized spalling, the reinforcing being exposed, we recommend concrete repairs and application of a coating system, at least on the areas where the paste has been eroded, the surface of the concrete has been eroded, to apply a coating system. And we recommend that work to take place in the next 3 to 5 years. That takes us now to aeration basin number 3. Again, we see the pictures demonstrating the biological deposits and the staining due to the wastewater environment. We also see above the water line, the paste being eroded, again with the bacterial activity, right moisture, right oxygen, the turbulent water, because the water is actually aerated, and we can see that erosion taking place near the water line. But towards the bottom of the wall and on the slab at the bottom, minimal or none so occurring. On one area of the aeration basin, we did talk to plant staff. There was a repair that was done in the past. So we noted that because that was isolated delamination, you could still tell that needed to be repatched as time goes on. So we noted that and we circled that there because you could tell that good bonding is really not there. And we probably need to take a look at that later and fix it. Then there was localized concrete cracks. very minor, but they are spaced every 8 to 12 feet. And again, for a structure that big, temperature and shrinkage effects are coming into effect. And so the concrete likes to shrink and contract because of the temperature changes. So for aeration basin number 3, what are we recommending? We did all our non-destructive testing with all our equipment, and it reveals that the reinforcement is not actively corroding in the areas of the walls and slabs that we tested with all our equipment. The cover depths also from our equipment testing also show that the walls, we have about 2.8 inches of clear cover. We talked about having a minimum of 2 inches from the face of the rebar to the face of the concrete. We have 2.8, so that's good news. And then at the slabs, we have 4.8, so that's also good news. Then with the laboratory testing, we did 8 cores. We tested 8 cores specifically for the various lab testing that we talked about earlier. We start with compressive strength. We talked about the load that the concrete needs to see before it crushes it. And so that load here for this particular structure is 4,700 range to the 8,000 pounds per square inch range. The minimum we want for this structure documented on the design drawings is 4,000. We exceed that, so the structure has structural capacity to hold. Carbonation depth, we have 0.25 inches. When we looked at that, we talked about carbon dioxide attacking the chemicals in the concrete. We have 2.5. Our clear cover is 2.8 at these walls, and so that's also not of concern. And then chloride concentration, when we did all our chemical testing in the lab with the amount of chloride ions in it, we are coming to 350 parts per million, which is the benchmark. You want negligible risk. And so the structure is not at risk from chlorides. We also did one more thing here, petrographic examination, because this was one of the structures for the in-depth assessment. And we could see that the first 0.1 to 2.2 inches was deteriorated due to the sewage attacking the face of the concrete. And we saw that in one of the pictures where the piece was being eroded. But again, it's not to the cover. We had enough cover to be able to get things to look good or work. There's another reaction, though, that we do want to check for with these structures when it comes to petrographic, because that's the cracking that you don't see to the naked eye. It's cracking that you usually see under a microscope. And that reaction is called ASR. ASR, alkali silica reaction. Very simply put, cement, as we know, as we said, is very alkaline, not acidic. And so there are hydroxides. These are particular chemicals in the cement that make it act that way. Unfortunately, though, with the aggregates that we get to make our concrete mix, some of the aggregates sometimes have silica on it, which is another component. Or some of the sand will have silica in it, another component. What happens is the chemicals in the concrete, these alkalis, react with these silica material during the concrete mix process. When they react, they form that white gel that you see. You can see it under a microscope. That white gel stays on top of the aggregate and between the concrete paste. When you come in contact with the water, that gel swells. And when it swells, it's going to crack the structure. And so with time, you have these fine line cracks that occur. And when the alkali is still present, it will continue to eat it up because the silica is still in there. And until the alkali is gone, that reaction continues. Well, for the aeration basin, we observed that we did that in 3 cores. And the micro cracking, 1 out of 3 cores was observed there. And so we are showing that picture there to show that. However, though, for this structure, it's been in service for about 30 years. And so we are going to compare that to what the alkali silica reaction, the crack pattern looks like in comparison to the structure. For this structure at 30 years, ASR evidence is really minor, although we saw it in just 1 of the cores. Here's why we say that. The picture on the left, on my right, I should say, is a typical structure, not SGRE structure, but a typical structure that has the crack pattern when you have ASR present. Some call it spider cracks because the cracks are all over the place usually, and you can't really stop it. However, the aeration basin is nowhere near to that. And so we can say that it's minor, especially for this structure that's been submerged for 30 years. That's the scale that it ranks on. So what is our recommendation for the aeration basin? Again, visual observations every 3 to 5 years to take a look at that visually and see how that structure is still performing. Then non-destructive and lab testing, which we talked about every 10 years. And then we are recommending those areas that are delaminated. We saw the earlier repairs. We said the voids are likely there. We need to concentrate on it. And then also the paste on the surface being eroded there, applying a coating system. We recommend that work to take place in about the next 3 to 5 years. Let's go to clarifier number 2. Again, same thing with the staining and biological deposits on the clarifier. We see that in the picture. And then we see the paste also being eroded towards the surface because of all the turbulent waters happening there with the moisture and the air right environment, and then bacteria. So all that takes place there. But it's approximately 1/8 of an inch on the near surface. At the clarifier number 2, though, it was coated. So we looked at the coating, and some of the coating is laminated. Laminated is where the coating kind of is beginning to come off like a sheet because the bond is no longer there to hold it. And so we saw that on the clarifier number 2. And also spoiling of the coating was also evidence in some of the areas where the wall was cracked. We see a sample of the crack of the wall. This occurs about every 60 feet. You see that localized vertical crack, and we kind of captured that also. So what did our non-destructive testing reveal for clarifier number 2? Well, the reinforcing is not actively corroding in the areas that we tested. All the handheld equipment testing data verifies that. The cover depths that it measured was 2.3 and 10.1. And in the walls, in these structures, we want at least a minimum of 2 inches. We do have that way here, and so we are good there. We tested 10 cores in the lab under the additional lab testing to verify the compressive strength, which we talked about, which tells us the strength of the structure. Again, it's well above the 4,000 mark, which is on the drawings. In this case, we're in the 5,000 to 8,000 range of all the cores that we tested. So the structure is structurally sound. Carbonation depth 0.13 inches, also less when we think about the cover, so we have enough. And then the chlorides are also below the 350 parts per million. And so it's considered negligible risk. Well, there's the good news, the petrographic examination, no ASR was observed. We talked about ASR earlier. All the 3 cores we looked at here, no ASR was observed. Under the microscope, 0.16 to 0.2 inches of concrete was deteriorated. So the clear cover was 2 inches. We have a little bit to spare with. And so we are recommending the coating again. So again, same thing, recommendation, visual assessment every 3 to 5 years, lab testing every 10 years with the non-destructive testing, and then the repairs and the coating system protects the cover of the concrete in the long run. And that work we recommend to take place in the next 3 to 5 years. That takes us to the lift station number 2. We break it down into 2 parts because we have the wet well and then we have the dry well portion of this facility. So in the wet well, very aggressive environment. That's where the waste is initially coming in. And so we see widespread staining, biological deposits, especially at the top where you have the right amount of oxygen and moisture buildup and the bacteria is very active and aggressive. Given of this acid to attack, we can see that they result in the paste erosion that we are seeing on the right, quite extensive, at least at the top 2 to 3 inches. Towards the bottom, very much less because that's also managed, but at the top where the environment is aggressive, above the water line, that's very visible. At the openings also on the top slab there, we also saw some visible cracking right there. So those cracks also were evident at those reentrant corners in the openings at the top slab. But at the bottom though, it looked very good. There were no audible delaminations, audible. So when we sound it, where it gives off that hollow sound behind it, we didn't see that at the bottom. And so the bottom of the wall at the wet well is in good condition. What did the non-destructive testing reveal? Well, the reinforcement is not actively corroding. When we use all our handheld equipment to measure, we could tell that. Then the cover depths, again, face of the structure to the reinforcing, we are getting about 2.6 to 9.3 when we look at the walls and the slabs respectively. Minimum we want is 2 inches, and so that's also good. For the lab testing for this one, we did 8 cores, we examined them. And so concrete capacity there, we looked at a compressive strength, which we defined earlier. That's between 6,000 in the 6,000 ranges. Again, well above our 4,000 minimum average that we typically see for structures such as this, and that was also documented. Carbonation here was negligible, and then chloride also was negligible, and so that's good for this structure. We show a picture here of the reinforcing just to show when we say the reinforcing is in good condition. This is what it looked like. We can see that the reinforcing is in good condition, no significant corrosion on the reinforcing. It looks very much intact within the core. And then for the lift station number 2, there was no ASR present, so you don't see any of the whitish gel in any of the cores that we also took. So summary of the petrograph there we talked about. And then as far as the deterioration of the concrete on the surface of the cores, it was very minor compared to the rest of the structures. So again, similar recommendations, visual assessment 3 to 5 years, non-destructive and lab testing every 10 years. And then for the areas, especially at the top where we saw that massive, aggressive erosion, we recommend the concrete repairs and the cracks for that, concrete repairs and application of a coating system. And we recommend that work to take place within the next 3 to 5 years. For the lift station, since that's an aggressive environment, we also recommend that when we go in to do the concrete repairs, we should look at an additional in-depth corrosion assessment to see what we need to do further, if we need to protect the structure further, just to extend the service life of the structure for the long run. Then we come into the pump room, which sometimes we also call the dry room, because that's not the wet section. There in the picture on the left, we see some staining and we see a fluorescence in some of the wall cracks. What is a fluorescence? Really, when you have a crack, usually in the concrete wall or in a slab, water begins to migrate through it. As the water migrates through the cracks, it's going to react to the chemicals in the concrete mix or in the cement. As the water gets to the surface, it gets evaporated, and then it leaves behind these chemical deposits, whitish in nature. That's what that process with that deposit being left is what we call a fluorescence. Next slide will show a zoomed in picture of what one of them looked like. At the bottom, though, in one localized corner, though, we saw water ponding at the perimeter there of the wall. And that's likely coming from maybe leaks from those cracks or some of the pipe penetrations that go through the structure. So we also saw local coating being coming off the wall, so delamination, so falling off, peeling off from the wall. So we want to also address that. And that's the fluorescence, a zoomed in view, as you can see with the whitish substance being left behind as the water evaporates in that crack. What did a non-destructive testing reveal? No active corrosion, but it also showed that there's a lot of moisture at the bottom. The previous picture that I showed, we saw that water ponding, so it captured that's very moist at the bottom. The cover depths that it measured with our equipment, 3.8 at the walls, 10.7 at the slabs, we want minimum 2 inches, and so that was good. We also tested 8 cores here. We are in the 6,000 range for the compressive strength, well above our 4,000 mark for concrete, and so that is good. Carbonation is at 0.63. We have enough cover to accommodate that, and the chlorides here are also negligible. So again, petrographic examination, looking under the microscope, what do we see? No ASR were observed in the 3 cores that were tested. Concrete here, no deterioration, that's the dry portion, and there are no other mechanisms for cracks that we saw in this segment. So recommendations, 3 to 5 years, visual assessment, just like we did, see if anything is changing from these structures. And then we also recommend in-depth analysis every 10 years. And then the areas where we describe the fluorescence, we describe the minor cracks, we want to go in and fix it. We describe the areas whereby the sewage is probably affecting it, just like the wet well, we want to go ahead and apply a coating system when we do this work. And our recommendation is in the next 3 to 5 years. Last slide shows a summary of all our testing and all the analysis that we received, yes or no, to identify the ones that had any additional work or lack of, or where we had other recommendations also to make.
Plant capacity assessment. Yes, we can, but I thought this would be helpful for you all to understand, because the existing plant condition or the assessment of an existing facility is not only condition, but it's also condition plus the capacity.
You can all say, hey, that makes sense. So much into a capacity. Yes.
Sure, we can take those questions.
Questions the area.
We have noted the questions downstairs, so we'll definitely come back and bring back the slides, if that makes sense.
No, it does.
All right, so as I mentioned, the existing plant capacity is equally important when we are looking at the assessment of the treatment plant. Because we are not only looking at the condition of the assets on the ground, but also whether those assets can treat the capacity or the flows that are coming through the plant. So how do we go about doing the capacity assessment? We are looking at two main components: incoming wastewater flows and the water quality coming into. So what is the load coming into the treatment plant? And what are the TCQ permit requirements is what's coming out of the plant. So both incoming influence into the plant and what's going out of the plant helps us assess what the treatment process needs to be and how big of the process it needs to be to treat and meet the TCQ requirements. So first, we'll talk about the wastewater flows and loading that's coming into the treatment. We looked at the data over the last 2 years, from 2022 to 2024, to understand what the average daily flows were at the site, what was the max month flows, as well as what the peak 2 hour flows were at the treatment plant. And then, so the first column you can see, it shows you the historical last 2 years data, the average of that data. The right-hand column, the evaluation criteria, is what is from your master plan that was developed for the treatment plant, which shows that the average daily flow of 7 MGD and the peak 2 hour flow of 28 MGD. And why that is different than the last historical data is in the next slide. The FCRA has already committed to provide wastewater treatment services based on the facility plan. So this graphic is from your facility master plan information, which shows you the existing plant, 10-year plan, and the build out. As you can see from this graphic, 1.7 MGD is already purchased SFDUEs by SGRA, which means those could come into effect anytime. So we need to plan, or our assessment evaluation criteria is based on what was recommended from the master plan, which is an average daily flow of 7 MGD and peak 2 hour flow of 28 MGD. This is the table showing the loading of the treatment plant. So what is the BOD coming into the plant? What is the TSS coming into the plant? What is the ammonia coming into the plant? The nitrogen and phosphorus. Again, the first column shows you the historical averages over the last 2-3 years from 2022 to 2024. And our evaluation criteria about what the processes should be treating is the right-hand column. And that is based on the historical data plus 10%. And the 10% is added as a safety factor over time to make sure that it can treat whatever fluctuations the plant receives over time. Now let's talk about, we talked about what's coming into the plant. The TPQ requirements, what are the permit goals of the treatment plant? This is the TPDS permit at the outfall number 2 is the right-hand column, and the first column is the outfall number 1. So this plant has 2 outfalls. Both have different permit requirements set by TCEQ. As you can see, the outfall number 2 has more stringent requirements in terms of the BOD, TSS, ammonia, and NO, dissolved oxygen. So we wanted to make sure that the outfall number 2 can still meet the permit requirements. So our evaluation criteria for this study, we are making sure that we are using outfall number 2 permit requirements as the evaluation criteria. So again, as I mentioned earlier, we talked about the wastewater treatment influent flow coming into the plant and the loading that comes into the plant and what the TCQ requirements of outside the plant is. Now let's talk about the treatment process itself. Can the treatment process treat what's coming into the plant and still meet the TCQ requirements? In order to do that, we look at two specific things, the process capacity and the hydraulic capacity of each of the process areas. So the process capacity is the ability to treat the wastewater flows or the loading to meet the TCQ 217, Chapter 217 criteria. Hydraulic capacity is to evaluate, it looks into evaluating whether each process area can convey the peak 2 hour flows through the plant, regardless of what the process capacity is. So can the water flow through each of the process areas without submerging the weirs or overtopping the walls of each of the structures? So let's talk about that graphically. The y-axis is the flows in NGD. The x-axis shows you different processes at the treatment plant. So it shows you from influent, screen, influent lift station, drip removal, aeration basins, secondary clarifiers, filters, chlorine contact basins, and the effluent meter and the storm pumps. Those are the processes in sequence, how the water comes into the plant and how it's getting treated. The black line is the permitted capacity, the existing permitted capacity of the treatment plant, which is 18 MGD, the peak 2 hour flow. The top yellow line is the evaluation criteria we use for this study based on the facility master plan recommendations, which is 28 MGD peak 2 hour flow. So let's look at the process capacity first. The process capacity, again, was calculated based on what is coming into the plant and how can these processes treat it. So we used a biological wind modeling, biological model to calculate what can be treated by each of these process areas. As you can see, majority of the process areas can meet your existing permit requirements, except the filter and the influent lift station. Influent lift station currently cannot meet the permitted capacity of 18 MGD peak 2 hour flow. However, majority of these processes does not meet the evaluation criteria of 28 MGD peak 2 hour flows, which shows that there is a delta that we would have to build additional processes, additional clarifiers or filters, build potential influent lift station capacity to meet the evaluation criteria. Now let's look at the hydraulic capacity, which is again, just pushing the water through each of the process areas without submerging the weirs or overtopping the wall. We are not looking at the process capacity or performance of the process area. As you can see from that graph of the light blue bars, the aeration basins and the filters currently do not meet your plant permit capacity of 18 MGD. And that is because, as you're aware, the aeration basins 1 and 2 are not in service because those are not structurally sound structures. The light blue bars also indicate from the evaluation criteria perspective that the influent lift station, aeration basins, filters, chlorine contact basins, and the effluent meters do not meet the evaluation criteria of 28 MGD peak 2 hour flow as well. Now let's look at what the alternatives we were evaluating part of this study. As part of the study, we are looking at 4 alternatives. The first is the repair in place alternative, which is basically looking at the condition, as you just heard from Queasy and Felicia from last month. All the repairs that are needed to make sure the existing assets are structurally sound and can function, plus the capacity requirements needed to meet the evaluation criteria of 7 MGD average daily flow and 28 MGD peak 2 hour flow. That is our alternative 1. Alternative 2 is replace in place. 3 is the new conventional wastewater treatment plant adjacent to the existing plant. And 4 is the new MBR plant. So looking at what this is, again, laying out the first alternative. And as I mentioned, there are basic assumptions that went into the study. One of the assumptions was that we will not ask for any of the variances by TCQ for any of these processes. And that was to make sure that we are comparing apples to apples. All four alternatives, we are not asking for variances from TCQ. Second, based on the capacity assessment and the condition, we came up with what repairs needed to be made at the site and which new additional facilities needed to be added at the site. So the influent lift station, since it does not meet the existing requirement, we do need to build a new lift station because the existing electrical buildings of the existing lift station cannot support additional pumps. So as you saw from the graph before, the existing lift station does not have capacity to meet even the current permitted capacity or the future peak to our flow capacity. We cannot just add a pump in there because the existing electrical system, the MCCs, do not have the room to add additional VFDs or pumps. So we would have to add a new additional building with them. So the general assumption going into all four alternatives is we would need a new lift station for under all four alternatives. The admin building, the maintenance building, the fuel station, the stormwater detention pond are some of the common structures that would be needed under all four alternatives. Again, this is showing repair in place, replace in place, where you are taking one structure at a time, one process area at a time, replacing it and building it. So the construction schedule, of course, is going to be much longer for alternative 2 than it is going to be for alternative 1. Alternative 3, again, the layout shows a brand new conventional treatment plant adjacent to the existing treatment plant. Alternative 4, this is the layout of the new MBR plant, showing again, very similar to what you have previously seen from the previous study, using some of the common structures as I previously mentioned. The next steps for us, our job next few weeks is going to be completing our net present value cost estimating for all the four alternatives. Complete the evaluation of all four alternatives. You all have seen the criteria, evaluation criteria. We would be completing that evaluation based on those evaluation criteria and your weighting that you guys have developed. We would use those two pieces of information and evaluate each four alternatives against each of those criteria. We would come back next month in May and present those alternatives evaluation process, how we did it, what we did, and also the results out of that evaluation. With that, now we can take any of your questions you may have. So let me get you all the mic. So Mr. Brad, this first question.
Brad.
You want to go back to the bar?
Where's Brad?
Over there.
Oh, there you are.
Taking questions.
She has a list of everybody that raised their hand for a question, and we're gonna go through the slides.
Yeah, slide 6. First off, great presentation. A lot of really good engineering work been done. Appreciate you taking the night to update us on it. Okay, I'm Brad Hound from MUD 7. I want to say thanks so much for taking time to present this tonight. A lot of really good technical work. A couple of questions on slide 6. So you refer to remaining useful life values were calculated. I did not see them in the presentation. Granted, I didn't read every page of the technical reports, but I didn't see that. That seems like that would be something that would be very useful for us. This had the check mark on it saying calculate new RULs being completed. Do you have that information? Okay, so this piece of work is not done. That check shouldn't be there. Okay. So the other one is there was no specific information on what target useful life you were using to generate your recommendations. So you had recommendations, but you didn't say what the objective was. So was that recommendation to achieve a 20-year additional useful life?
It would be less, on the lesser side, higher side than for, comfortable, right, the IUL part of the substation. So we have to now go through that. So between that 60 to 70 years, what has been spent, now we know what WJ recommended, so we can take their recommendation, subtract that, give us the.
No, that doesn't answer my question. The question is, if you do the recommendations that are on each structure, does that get you an additional 20-year useful life? Thank you.
Also on, yeah, wait, push the button. Yeah. Yeah, well, Brad asked one of my questions. The other question I had was indeed with prepare list of repair and place recommendations for the base case. Was that just a summary? I'm sorry. Yeah, of course. On your fourth bullet point, Brad asked about 3, and I just want to clarify on 4. Are those in place, repair in place recommendations for the base case, the ones that were in the recommendation slides that you presented in the presentation? Yes. Okay, so I'm hard pressed to understand how bullet points 3 and 4 have not yet been finished, but you could give us a map and tell us that's the repair in place plan. Seems to me you have to go through and do all that work before you can give us a map and says, hey, look, this is the answer. Because this map and this work is going to develop the case that you're going to run to do the economics, correct? Yeah, well, that's my next point, because you had that as your 5th bullet point on slide 6, and you gave us 1 slide. So I got detailed reports on the condition assessment, made good sense. It ties to your presentation. Then you throw a couple slides there, which I don't understand, and which had no justification back or any support technically to tell us how you got to those numbers. And yet you build a map that's going to have a lot of new structure on it. I'm at a loss to understand how you came up with that and why you didn't present that to us. I think what my bigger point is that I'm probably relatively new to the process because I missed the first couple of years. We had 3 cases built in detail, and this fourth case that you're helping us with is a newer case. And yet we don't have the detail that builds that case so that when you present to us next month, which is going to include an awful lot of stuff. It's going to include the matrix and an NPV. It's going to be an awful lot of detail, but we didn't get that in this meeting. We got a good understanding of the structure. Thank you. I thought that was an excellent report and it all made sense to me. But then we're going into building new structures and a new plan that's going to actually be the majority of what we're going to have to pay for at the end of the day. And I have no detail on it whatsoever. You have nice pictures on a map. It's, oh, we need a new aeration basin. We need 2 new clarifiers. There's no detail to support that. And it's very hard for us. I'm worried that in a 4 weeks, you're going to dump all this on us, including the decision matrix and the NPV, and it's not going to, we're going to be busy trying to make sense of the basic data that we should have had this month.
Your microphone. Okay, my microphone. Okay, I have a question about remaining useful life. So a number of, I gotta press the button?
Stand up.
Oh, stand up. Oh.
We don't have a read.
Okay. So, a number, so I have questions about RULs. So a year or so ago, I read a document published by the SGRA, which detailed out by asset tag all the remaining useful lives of every asset tag they have. Is that the base document that you're using to establish the remaining useful life, that document that SGRA has to pay for?
Previous report, we were reviewing and we were to go out into the field to compare our field observations with the remaining useful life that was in the report. So that was a reference, but we were using our on-site assessment to understand from our point of view, how much life is remaining on your assets. Does that answer your question? It's the point of reference, but we were using our observations
I see.
from that in time.
So I guess my observation is, if you go back to that report, it's a single statement. It's a pump. It has 7 years remaining useful life. It gives no more detail than that. And you know as well as I do, any moving equipment, which is, this organization is packed with it. Oh, so any moving equipment, right? Depending on how often it moves, you know, it turns and twists. It has a unique useful life. So in that document, it just says it has 7. It doesn't tell us anything about the condition, the age, the date of installation, anything. So I'm just curious how you can establish a remaining useful life with the beginning input is an asset tag number with the statement that it has X years useful life. So I guess I'm a little concerned that we're taking shortcuts.
It's based on how we've, and that's the we that we're working on. We've done the assessment, we have our note, now going to define it and document that and send that out. That's going to provide the background, so it's not just, oh, it's a 7. Why is it a 7?
And that'll be all those asset tags, the 108 for mechanical. I mean,
Yes.
electrical's a little harder, but
Yes.
okay. Thank you.
I looked at the previous proposal of the wastewater treatment plant. My understanding is that the capacity was much less than what is your assumption here today. that it was a smaller plant with less capacity, and all of a sudden, this new plant is going to have more capacity. So I guess I want to know how you got to that number.
Like, look, because facility master plan, 8,000 draft. Where we total the need.
She wants the slide to kills. Trust me, it's up.
This graphic. This came from the facility master plan. The bottom blue bar shows the existing capacity or the utilized SFDUs by SCRA. 1.7, the hashed block, is the purchased SFDUs that are currently potentially, even in some cases, constructed. They're just not being used because, for example, some of the buildings in Woodlands area are not occupied yet. They have the buildings, but they are not occupied. The SCRA is supposed to provide the service for that 1.7 MGD gas line as well, which would come into effect next week or next month or a year from now. We don't know. But that is already sold as a DE. So SCRA is on book to provide the capacity for that 6.06 MGD as of today. And there's a buffer of 0.9 no gas case. But SGRA is supposed to provide that capacity. This is where we got those numbers from. As of today, SGRA is supposed to provide that 3.6 plus 1.7. And their offer that is total to 6.06.
So that has changed, is what you're telling me.
No, that has not. This came from the facility master plan that was a couple of years ago. So that has not.
We're doing.
So can you compare that?
I'll
No, you don't. It's not your fault. They're doing the bait and switch. Yes, they are. Their assessments.
They did change.
Told you we should have had this separate.
They did change.
There's kind of two questions. What's that? Is it okay? Okay. Yeah, great report. Really appreciate the information. Two questions kind of related. On page 2 of the detail assessment, it says, the sentence says specifications of the original design were not available and therefore were unable to establish the design basis concrete material properties of each structure. Now you went through all the structural testing and all that, and I think I heard you later on. It kind of said we feel good about all the concrete, but what was that sentence kind of meant to tell us, and why is that important to put into the report? That's my first question.
Yeah, in particular for that, our photographers are looking under the microscope.
Right.
We're able to evaluate what the water cement ratio might have been, or the coarse aggregate size, or the sand that was supposed to be used, any of that. We don't have that original specification to compare it to. We feel confident in what we saw, and we can, everything we have in our report to say, hey, here's what we had, water cement ratios between 0.4, 0.5, all that kind of stuff. We can't compare it back to a known design and say, oh, it did or didn't meet the original design intent.
Okay.
That's all.
Okay, good. It looks like pretty
For good
good.
purpose, does it really matter?
No, you just didn't have that to start with.
We didn't have a starting point.
Your testing looks like it's still pretty good concrete, right? It's
Yes.
got the testing strength you need. All right, the second thing is around, so the assets that weren't studied, all right, we picked a few here. And I think you said, Kwesi, that you thought that this selection of structural components that you're going to test was a good representative sample. How good do you feel about that? And give me an example of what I want you to address directly, which is, I think it's, is it clarifier 3 that has the bulging wall, the famous bulging wall, the one that. The Bathan 3, okay. How good do you feel about this correlation from one asset to another, the one you tested versus you didn't test? And how confident should we feel that there's not some, problems with just drawing that assumption to the rest of the asset base?
Very, very, very good question. So what we did was we sat down and we listed all the structures and we have the drawings, and so we looked at, okay, which year did these sets of structures belong to? Right, so that's the age piece of it. And then we also looked at, okay, for example, the field report of the one that was bulging, that's the Ration Basin 3. So that's in what you mean for the worst case condition. So for sure, we wanted to test that. So we selected the Ration Basin 3. And then the size of it, just the sheer size of it, is one of the big structures. So you sure want to test that. And that correlates with some of the structures that were constructed around that time frame, around that year. So we looked at that piece of it. So very confident, because to be representative of the concrete mix that was used during that time, right? Because we don't have a specification to go to, we have the drawings that tell us, but we want to verify it. So at least with that benchmark, we are confident. And then we pick other structures, because as a structural engineer, you design the different structures different. So I picked a square one, but I want to pick something not square. So I picked a circular clarifier, which was also constructed at different time. So it would likely have different properties, and that will correlate with some of the facilities. So for each of the facilities total, we just group them into this is the drawing set with this is the drawing set with that, this is the drawing set. Let's make sure we picked representatives from all of it so that we are very confident that we've captured it. And then from a visual assessment, which ones had more cracks than others? Those people candidates, which ones did we get reports from the staff about this bulging wall fixed? Those were good information to have. So that really helped us to kind of narrow it down to pick some good selected structures.
So we should feel good about being able to extrapolate this information to the other structures and have a high degree of confidence in that. That's what I'm saying. Okay,
Absolutely.
all right.
And the data so far, it correlates.
Correlates, okay.
As far as the fight, if we saw like some unique variations, then we'll start saying, wait a minute, let's pause the dice and kind of take a bit of something. But it really correlated. That gives us full confidence. And we look back in the codes, right, for those areas where it was constructed. That's why like the 4,000 benchmark is critical, because that's what was used back then. And even until today, the minimum is 4,000, right? So those things give us like a good feel for the good work that was done.
Perfect, thank you.
These are the same structures that we talked about in January trustees meeting.
Yep, I remember, yep.
We move to slide 18. And then Mr. Smith.
Slide 7, you identify repair phase candidates for base case. You mentioned structural, mechanical, electrical at IMC. So I take it structural is going to come from you. And the rest of it's going to be the increase in difference reports?
No, everything is coming from us.
Oh, okay. Thank you for clarifying.
Did it as well, but the detailed assessment, lab testing, WJE testing, the WJE's report only appendix to our assessment.
Okay, so you're still doing the mechanical, electrical?
No, you don't have it yet. That's the report. That's the report that we're working on. That's the report we're working on. Slide 18.
Folks.
And we have Mr. Davis.
17.
17, 18.
Yeah, so you, oh, maybe you have the wall. Oh. You talked about this, the CMUs, the concrete masonry units. And you recommended repair of that CMU replacement. And what's the advantage of doing CMUs versus concrete?
Especially in a wastewater environment, it's very corrosive in nature. It will eat it up, and we are looking at the longevity of the structure, extending it for not 1 or 2 years or 3 years, but want to extend it out further. With the concrete, get that capacity for a longer time. If you notice, I think, just out of the
Yeah,
picture.
it's difficult to see here, but these original walls where the dumbbell kind of columns are, it's like this dumbbell kind of shaped structure of the square, the wall and the square. That's all concrete. It's these supplemental wing walls that were added later that are CMU. So it's not a whole lot of the walls that that are CMU, but there are portions of them. And my hunch is, CMU is cheaper to build, for sure. There's no reason to do it. But yeah, that could be replaced. It's not the entire structure. There's small portions of the walls.
And then see, they go to the, I think the next slide I thought it shows. So you can see, you can easily chip it because the corrosion effect, you can just take a sharp object and then it just come out. And we just want to make sure that we give the recommendation that extends the life of the structure. This is something you're gonna have to go back in the next couple of years. And you're facing the same thing because of the street.
Taylor, I had a question in this slide 18.
I don't think. Probably that.
Sure. Oh, yeah, to your misfortune, I'm afraid. Yeah. I'm gonna have a question on each of the summary slides, and I think I'm addressing it to the structural concrete guy, because at the end of the day, when I read your technical assessment report and I listen to the presentation, I think it's clear, but I want to ask you, is it true that when I read the chlorine contact basin summary, that structure is in pretty good shape and should last us 20+ years? Yeah. Thank you. Yes, well. Yeah, with repair, true. And this condition on the right, we didn't do the acid attack. We did not do our non-destructive testing in this structure. So I can't really tell you what the cover depth is to that steel there. But some of the modifications that were done over the years, where they cut off walls and make openings for the water flow. That's where we saw some of the cover depth that was exposed. But in these smaller walls here, like the wishbone wall we were just talking about, I don't know what that cover depth is. So within the next 20 years, I'm saying, hey, if this continues, I would be saying, hey, no, you need to repair, you need to do this resurfacing and coating repair to repair this concrete. And really the lift station, I know I'm getting ahead of our questions here, but lift station 2, that area above, those are the two ones, from my experience looking at existing plants, say, okay, these structures last another 20 years. This and the lift station condition are the two where I'm saying, hold on, you gotta do something with the next 20 years here. The other conditions, I think, yeah, as you went through and the recommendations, like those are all good practice, good things to get you good durability. If you don't do something with this, and you don't do something with the lift station, you're gonna have problems. But otherwise, yes, these structures, nothing I saw on any of them that say, hey, we need to tear them down today.
Thank you. No, good summary.
Is there anything that we could have done, leading up to how
repairs up until now, from inception till now, that could have avoided some of these issues that we have now?
Yes, so I think these visual observations every 3 to 5 years,
All right.
non-destructive testing, especially in these structures that we haven't done one yet, pouring contact bases. Doing something like that, and I know I'll live the hundreds of pages you guys got. I mean, I know that's not all cheap, but relative to replacing a structure, by doing those types of things and the visual stuff to be quick to, that's a quick look to be able to say, okay, how are things progressing? And then, yes, just like you're not known, if you do the repair earlier rather than later, it gets more expensive the longer you wait. So particularly in the pouring contact basin and the lift station. Now, by design, the lift station has a lot of cover depth, so you haven't exposed the bars yet, and no real structural issue yet. That's part of the original design, is to have more cover to fight that acid attack, to let that concrete deteriorate.
Right.
But yeah, you could have done that 20 years ago and mitigated it. Some of these coatings that are that Fozzie's got on the other structures, where we're only seeing 1/4 of an inch. You don't have to do that right now, but if you do, now you're getting durability like it was a newer structure.
Right.
Do it. But yeah, you can catch these things sooner rather than later, for sure.
Should be like a 5 and 10 year or something like that basis, where we drain the tanks and then do some recoating.
Right, particularly the and lift station 2, where we showed up, it was, hey, we need you in and out of here quick because we got to use these things to operate our plant, right? So I get that's not an easy thing for me to say, hey, every 5 years, drain the tank and look at it.
Right.
Some of the structures maybe are a little more redundant and do that. So yeah, particularly on those ones that are real critical, means they don't get shut down a lot. Maybe you can't achieve that every 3 to 5 years, but those are the ones, because they're critical, you want to look at them.
Thank you.
That was a good question.
Slide 21, Mr. Leiter.
Fred Levin, I'm with 146, and I've got a couple of questions and observations for you folks. first, building off Brad, John, and David's comments on the remaining useful life, it would be interesting if we could get a simple chart talking about when that asset went into use, how long it's been in use, how many years are left, the remaining useful life, and if we could take some type of preventative steps prior to this expiration of the remaining useful life. And it begged the question of preventative maintenance, because several times in your report, it was indicated that you could not do visual inspection due to paste, gel, whatever the case might be, staining and the like. It seems to me that 3 to 5 years for periodic visual inspection is a little long. Most PM programs, at least in a manufacturing experience where I come from, happens every 6 months to 12 months. And whether it's scraping, I guess the current technology is scraping, water jets. Some of my research talked about other processes such as impressed current cathode protection, chloride extraction, realkalization, and electrokinetics. And I don't know if any of that has been included in your thought process for not only extending the life of what we have, but looking at the new technology that's available, even in cement manufacturing process, because I did some research of current literature. And there was one article that I wanted to refer to you if you've not seen it or not aware of it, and I have it here someplace. Yeah. It was an article by Michael Bernard, and he did it September of last year. And he talked about the electrochemistry that makes low carbon cement and also makes it more solid. And it's in, let's see, the reference I got was Futures Electronics, and they referred to one company, Sublime Systems in Massachusetts, which manufactured this process. And if they have enhanced concrete production, coupled with those processes that I mentioned earlier, that could be used to help mitigate the issues, not only of the chemical reactions, but also of the bacterial and the anaerobic and aerobic organisms that grow. It could be helpful to expand even to a further length of time. One more point to make, if you can go to the chart that talks about existing 10-year and build out or capacity. It was 3 bars. Here we go. Great. One of the things I've done probably too much research on SFDUEs in the last 9 months, but my concern here, we have an existing number of SFDUEs that have already been purchased by all of the MUDs in this room. We have excess SFDUE capacity that have not yet been utilized or sold. My question is, have we overlaid the future growth plans of the Woodlands Township to this chart? Because if we're taking a look at the normal progression, history is not a good indicator because we've grown too fast. But going forward, with as little land that we have left for development, I think it's 760 acres. And in talking to one of the developers, the largest one, they're not pressed right now to make commitments to build on a large scale for that 760. In the interim, several MUDs, or at least one MUD that I'm aware of, have taken a look to expand their geography outside the Woodlands Township with defined areas, which is allowed by state law. So my question is that included? Because that takes away from 2 things. Number one, our charter for the WWA to only service the Woodlands Township. And secondarily, what is that pressure adding to the river authority's ability to service this not only forecasted growth, but this unforecasted growth with defined areas? And I'm concerned about that because we're only building to a certain level right now. And if we're now looking at a multiple, whether it's 10% or 40%, 30 years out, none of us will be in the MUD meeting, but that's the point being, it will affect the future of our community. And I just want to at least get that on your schedule to at least be aware of that and to consider it in your planning.
I mentioned our study, sir, that what was indicated in the master plan, that 7 MGD average daily flow. But I'll definitely make a note of the future roads as we talk about.
Great. Thank you.
So that's part of our coding recommendation, corporate judgment. Yeah, with the right coding recommendations to use for the right work. What the right comfort return materials to be everything is better, with not sharing dollars from the comfort makes and I think that's what they're only going to all of the information.
Mr. Taylor, you had questions on each of the recommendations, like some they address them, or do you want to get that?
You can summarize it well, saying that all the assets that's structurally evaluated in detail report in the presentation, that they're all in pretty good shape with some minor exceptions of the lift station, wet well, and which other one was it? Right. Thank you. And I needed some coating and repair work. For 20 years, some coating and repair work sounds pretty good to me for 6 structures. Thank you.
And just to reiterate Bart's last comment, we made recommendations that include some of the calcium aluminates and some other materials that are.
Yeah, good stuff.
Mr. Smith, yeah, this question was like for you. Recommendation.
I had one before that too. Let me ask you that first. You have carbonation, chloride concentration, less than 350 ppm. 38, yeah. And what's the most of these things you're saying, cement coverage of 2 inches or more. What's the minimum maximum of that you look for in 350 ppm?
That's when that protective layer over the steel can start to break down, and now the reinforcement can corrode. If the chloride concentration goes above that, say 500, 700, 1,000 ppm, it's much more likely that things are going to be corroding. And we were a lot lower than this in most of the structure.
Okay.
Sure.
Okay. Now lift station. Yeah, lift station. So Ed, I'm going by memory here. Sometimes you forget. So I remember looking at a 10-year plan. It was probably 3 years old. And in it, you talk about the rehabilitation of lift stations.
Yeah.
And you had like 2.7 million or something like that to rehabilitate. But I thought that was lift station 1 that you wanted to rehabilitate.
Lift station 1, and Chris helped me. I may need some your memory too. We had in the 10-year project plan to do some rehabilitation and set it aside until after these studies could be completed.
You did.
So that we didn't do something that would end up being wasted if a new station was built.
Right.
And remember, we're doing the optimization of lift station 1 and 5.
Right.
Now.
So when you were speaking, yes,
So both lift stations.
both lift stations are
Lift station 1.
2. Okay, I just saw one of them. I thought it was 1. Okay. You were talking about the reason to, rebuild, let's just say rebuild or revitalize lift station 2 because it didn't have enough pump stations. But lift station 1 has 1 or 2 more pump stations. And I thought that was the reason why you chose to rehabilitate that one versus 2. Am I missing something here? It's been a lot of years.
Lift station 1 is at the
Right.
We're proposing to decommission that and run a gravity line over to a trunk line. Take that lift station 1 out of service.
Okay.
I'm talking about primary lift station at the wastewater treatment plant, different story.
Here comes Chris.
Oh, I'm confused. I'm confused. I agree. So we have 2 lift station 1.
Ah,
That's the name.
Lift station 1 is at the corner of Groveland's Mill and Woodlands Parkway, which is another project. Lift station 1 and lift station 2 and this discussion are on-site lift stations.
That's the plan.
The project you mentioned earlier was to combine lift station 1 and 2 into one sole lift station.
Lift station.
1 and 2 combined into one new lift station.
One new lift station.
It has the bulk of the pumps. It has 3 pumps versus the 2 in lift station 1.
Has full pump capacity.
Lift station 2.
Two, and which has the spare mounties.
Is it
I thought.
2?
Lift station 2 has 4 slots, 2 pumps, 200 horsepower pumps in it, but there's not enough electric capacity in the electric.
To run.
And that's what was talked about.
Because the condition assessment for lift station 2, it was challenging for the operations team to not have the lift station up and running. That is the workforce. Had to go in and get it, create an assessment. Once they took the cords out, pour the concrete, wait for a little time and turn the lift station back on. If we try to rehabilitate the lift station, along with building new electrical building, it's going to be bypass funding for a very, very long time for the entire construction operation. This is going to be active for the operation.
Any questions? I 47, I know the recommendation side, I think so. Okay.
Yeah, 52.
Yes.
Oh.
Probably got the same thing.
Yeah, so, it's nice to see historical evaluation criteria. I guess I would like to see, current permitted, current design. And I was surprised to hear what I thought was your comment that the current plant can't meet its current permitted capacity. Is that your current conclusion?
Yes.
As you can see, this is the document.
How frequent is it?
What's the date?
Yeah, really.
This,
What date?
this, during, 2020, after phase 4. As you can see, documented flow is of, above. That was the upper meter limit. The document is on the chart meter that shows 31. However, the upper meter was converted, the partial was converted, so we cannot reliably say the true flow that was going out. So the capacity of the upper meter is short of 28.
Did we violate our permit during this time period?
Yes, for quantity, but not quality.
Okay.
Too much water.
Okay.
Over top weirs.
So we met our effluent quality requirements.
Quality just not.
Okay.
Consequence?
The violation from CCP with no monetary fines.
Exactly.
Yeah, how often did that happen?
So I'm not sure. I mean, it seems to me like you're building a design case for a 2-hour maximum flow. It's higher than our current permitted. And I'm not, and I also thought you said we couldn't meet our current permit. But I thought we could meet our current permit. So can we meet our current, is the kit on the ground adequate to meet our current permit?
You are meeting the permit. If your current permit is average flow 6 MPD, if you did see a 6 MPD flow, you would violate the permit. Because the aeration basins 1 and 2 are currently out of service. But the plant does not have the capacity to meet It's MGE, or that matter, seven MGE.
That's just an advantage, small investment.
And then
So the quality, yeah, the quantity, that's what MGE, that was the violation.
But that doesn't
The
have.
quantity, met all the parameters.
Well, but the aeration basins being out of service do not impact the hydraulic capacity of the plant. So I think we'll take this offline, but I think we're very, very concerned about the basis that you're using for your evaluation and how that's consistent, or inconsistent with prior studies and prior performance. Well, come on, that's not true.
No.
You just added new capacity, new units. The only way you do that was with the design. And what are you doing? You're doing a design based upon those, right?
But you're being disingenuous. You're saying you're not designing a facility, but when you're going to present in 3 or 4 weeks, an NPV of a plan for this so-called repair in place, it's mostly new in place, you have to include your assumptions. That's a design. And all that's being driven by, as far as I can tell, one chart that you've shown us without any detail or backup in any discussion from any of the MUDs as to whether it's valid and whether it makes sense to design a facility for that. It may, we don't know. And if you're going to dump this on us in 4 weeks, that's not long enough to understand. That's not going to work.
This was last year. What was the next question?
I got another question.
So is it common across that it's not? How does your man now use that? So, you're choosing a number, right? That is a rare event. Rare event, which the Texas Environmental Quality don't even find it for because they know it's a rare event. And you're using this as a basis to do a net present value.
The TCQ requires that the peak to overflow is 4 times your average daily flow. Average daily flow based on the master plan of 7 MGDs, 7 times 4 is 28-ish. So that's how we got to the numbers. We are not designing it for, are we?
This 217, chapter 217, right? Is this, it's been revised. Is this the standard that we fall under because we're grandfathered, if we designed the plant prior to 217?
Anytime you do major improvements on a process area, you would be looking at chapter 217.
So replacing a CMU wall, is that a major event? What, renewing a lift station, is that a major event? It would. So you have to make sure that lift station meets the new requirements. Okay. So that's the only 2 areas in which we have serious concern right now.
Yeah, question. Excuse me. I thought from the beginning, I going through the line, I've patiently not stepped up and asked the questions. Joseph Figueroa, we're on slide 53 and
Yes,
Felicia had taken it.
Yes.
But you didn't call my name out, so I've been patiently waiting for my turn.
It's your turn now.
I actually have this.
All right. Okay. Okay, great.
And then you right next.
Okay, thank you.
Yes.
Can you tell me, we had a presentation about peak flow. We had a presentation about peak flow 15 years ago. And there was I think the peak flow at that time was 18.5. Chris, you may remember.
15 years ago, so we'll see.
Probably 14, but what I'm trying to figure out is we've had the tax day flood, the Harvey, or we had Memorial Day flood, and then we had Harvey 3 years in a row. What was the peak flow in those? Do you
Right. I can tell you, I do not know that off the top of my head, but in the master plan that Mira has been talking about, in the Freeze and Nickel study, they do have a graph in there that shows all of the storms for the past maybe 10 years, maybe 15 years or so. It's around the Memorial Day tax day flood, and it shows what the actual flow was, where the permit was, and everything else.
Anyway, that peak flow crisis was 8.5. And I can't figure out, maybe somebody can comment where all this extra peak flow has come from in the last 10 years. And having a peak flow of 28 million gallons a day and these others. Does anybody have a comment? Any operators?
Trouble here. The TCQ requirement is that the peak 2 hour flow is 4 times. So,
That's something you sign.
so
So-
that's how we're training at the PDP. Because.
No, Yeah, I understand. But we actually supposedly measured more than 28 in last. Okay, so 9 months ago, which is, okay. I need to just gather some data. I need to look at it. But basically,
Thank you.
all is slow. Instead of 28. And we were in a whole lot less falls. We have. If it went.
But you will not meet TCQ
No,
requirement
but we're basing it on.
Get a variance.
unless you get.
Yeah, but the other thing is we could do, right now, we're processing about on a dry day, about 2.3 gallons a day.
3.3.
So,
Yes.
Thank you, Joseph Figueroa, Mud 46. I have a comment and then a couple questions. The comment, sure. I'll stand in front for this one. So I have a comment and a couple questions for you guys. The comment is thank you so much for the presentation. The content that you had at the beginning, the capacity assessment in contrast to your, the condition assessment in contrast with your capacity evaluation was markedly different, as you've heard from some of the members. The first half, you had quantified information that is consistent with Carollo's history. I did a little bit of background. You guys use computational fluid dynamics that quantify the Navier-Stokes equations for all of your modeling. You've used the Monte Carlo simulations, and some of the techie geeks here will understand what I'm doing. You've done factorial sensitivity analysis. So factorial would be an aspect of combinatorics, and the information that Kwesi was presenting, going down to the chemistry, if you will, the inorganic chemistry and whatnot, is consistent with Carollo's background of 90 so years. You were mentioning Mira, and there's a justifiable conclusion that you reach. And my takeaway, when I look at all of this content that was presented to us, there's a lot of data. A good habit is to distill. So I'm going to share my takeaways and then ask the two questions. The takeaway from the first section was, okay, we have 3 to 5 years where you're recommending that we do inspections. And every 10 years, we do more deeper type in non-destructive inspections. So my takeaway was frankly, all right, there's nothing imminent or dangerous here. And then subsequently, during the conversation, I heard that if we do those repairs, the repairs granted that were recommended by Carollo to do anywhere in the next 3 to 5 years, if we do them, that could extend the life, the useful life, another 20 years. Stephen, was that roughly what I heard? Okay, that was my takeaway. The takeaway from the second part, which comes to this slide, was look at this section here, SFDUE's single family dwelling unit equivalents.
And if you look at the fine print in this section over here, which says not currently constructed or occupied, my takeaway when I look at data and graphs like this is like, okay, so this is a projection. The red line is arrived at from, Mira, you said the master plan. And I think my takeaway was everything about the second aspect of the presentation hinged on how confident Carollo is on the information in that master plan that asserts that this number and these buffers are true. So what I would expect, and here we come to the questions, is can, for the next presentation, Carollo use their institutional knowledge, their background, to be able to come to a justification for the projections that's implicit in your assumption that the master plan contains the true and high confidence estimate of the, I saw the seven's up here. To me, this all hinges on how confident you are in the truth or the confidence levels. Otherwise, what we're left with, hey, trust the master plan we should be confident in. And I don't have that confidence. I understand numbers, and I understood the first part of the presentation and everything that backed it up. This seemed like hand waving. And I say this in the most respectful fashion possible. It seems like the consultants came, read the master plan document. The master plan document asserts certain things, and that information, while it may be true, is a black box, and I don't know. And so my request would be for the future to please do that. That's question one. Question two has to do with what you mentioned was the base plan. So there's an assumption of the base plan. And to me, when I saw an administrative building at the bottom right of the picture, and there was new land purchases, top left, and on the boundaries as well, that literally does not sound like in situ Latin, in place plan. So it seems like a contrast in terms. So my question would be also, if it would be possible for Carollo, when you guys present the next time, if you could break out literally in situ alternatives versus non-in situ. Yeah, the deltas. Thank you.
That's ridiculous. Depending on percent capacity, based on stall capacity. Stall capacity to who? 50% increase. We don't have, we're built out.
This is a modeling question. So as I come on board, I'm new. An SFDUE seems to be the unit of modeling that the different entities have chosen to communicate contractual obligations, interlocal agreements, whatnot. So I think that when you have changes in the oh, sorry.
No, go ahead, go ahead.
Okay.
I'm just saying that.
Changes in the definition of the SFDUEs ranging from as low as 320 gallons per day for all the way up to 416. I've seen differences throughout the years that you're talking right there from 300, say, to 400. That's a 33% increase in the definition. So when I see that, particularly when there's a multiplier around how many SFDUEs you have in total, a little change in the GPD, the gallons per day, could have a big impact that starts to hit the million gallons. All it takes is you have 100,000 SFDUEs, a 1 gallon increase is already 1/10 of a million, 100,000. You have 10 gallons per day increase for the SFDUE definition, and now you're 1 mega gallon per day difference. So I think it's like, that's crucial to know in terms of your data modeling.
We have information that has been shared, is also in the strategic plan report, and hopefully you have access to the Google Drive. It talked about where it was originally evaluated at 217 gallons per connection. And then during that strategic plan, it reduced down to 200 gallons per connection. But everybody has a contract with SRA for purchase SFDC. And there are multiple contracts for multiple purchases throughout the history of the league. And so we have sold capacity based on the current permit of 7.8 million gallons a day. And we're obligated to be able to serve that. Because every time a plant is filed with the county, that certifies the TCQ that there's capacity on the ground. Now, whether it's occupied or not is a whole different story. But the capacity has to be.
So let me add some comments here. History. I appreciate the new folks that went involved. There's a lot of work that went into the 7. There was another big meeting where engineering company presented all this, talked about the basis. What we need to understand is we are seeing a complete change for the basis of the new plant. Back then, the basis was what's built is falling apart. It needs to be replaced. It's reached the 50-year end of life. We have to replace it. The best way to replace it is to tear it all down and build a new one next to it. Okay? A number of us have challenged that. And what we've seen today is we were correct in challenging that because a lot of the structure is still in good shape. Okay? So what we've now gone from a condition-based justification for a new plant to a capacity-based justification for a new plant. When we had this discussion and we arrived at the 7, that was based upon the current fact that our current design and permitted is 7.8. Everybody said the current plant, if operated properly, can meet 7.8. Okay? That's why the messaging was, we're not building a bigger plant, we're only building a newer plant. We're replacing in kind. What has happened in the last couple of months is, no, we're not building the same plant, we're building a much bigger plant. Okay? Because what we've seen is Corella is saying the current plant can't meet the $7 million gallons a day capacity. And that's where we've changed, okay? This 7 is less than the current 7.8, okay? So I'm really confused with why we need all this new kit in order to meet 7 when we've been told the current plant can meet 7.8. I think with serious credibility issues, what is the basis for the need of a new plant? Was it condition? And has it moved to capacity? I'd like to get that answered. Because I think when we did that master plan, the alignment was, if we go from current 7.8 to 7, we can live with existing infrastructure, either replace in kind or maintain. There was no talk about we need to add new kit in order to meet future capacity.
But we also, remember, we were quizzed by several directors, the difference between chapter 317 and chapter 217. We told you all that the minute you go in and change a basin, we'll take the lift station as an example. The minute you combine the two lift stations into one, that kicks you into the 217 rules, which are a little more stringent than what the 317. We did indicate to y'all that aspect. And then we do have,
I would be seriously question whether TCEQ is going to make us replace clarifiers by us deciding to build a new lift plant.
no, I didn't say that. But you also didn't let me finish. But if we have a requirement by TCQ to have a 4Q 4 times the average daily flow for 2-hour peak, we do have an obligation to supply that capacity for the 2-hour peak. We've proven that we've gone over the 28 million gallons just by several storms that all have occurred within the last 10 years or so.
Withdrawal by hydraulics, not based upon contaminants.
I understand,
All the water we release is met.
but it's still a violation of our permit.
Yes, it is.
And so,
So are you willing to spend $500 million
no,
to avoid a non-monetary penalty?
but depending on how many times you do that violation, they may start finding because it may look like we're purposely ignoring their rules.
Have we had that discussion with TCEQ?
No, because we're not to that point yet. What you assume is that we're headed towards a new plant. We're not assuming anything. We haven't seen Mirror's results. You all have seen exactly what we've seen.
You bought a whole bunch of new kit in it.
All Mirror is showing you is the fact that certain processes don't meet the hydraulic capacity that's required by TCQ. That doesn't mean we're designing anything. You haven't authorized us to design anything.
Well, you can't do a process in the past design. Well,
Yeah, so I will say,
You got to have something to work from.
we need to,
Otherwise, you shoot holes in our cost estimate.
There's no detailed backups, what you're doing and what changes you're making and when we have to make them. And one thing is clear, it's saying about if we change a lift, if we change a lift station, we may have to do some other modification. Do we have to modify the whole entire plant to meet the new? Well, that's not what I don't see it. In other words, I'm asking for a schedule to show me if I move what basic critical pieces, what do I have to do and how much of this is required now?
I think we need that.
We don't have it.
Before we go to the voters and ask for more money.
We're not asking you to go to voters right now. What we're asking for is to listen to what's available. Next month, will be more information. The month after that, will be more information. Then we'll have a whole picture in front of you.
Look, we've seen a schedule that we're going to do this and the schedule says we're going to have to try to make a decision in a couple more months. And I think what our frustration is that we got a lot of information here that we've never seen before presented to us saying, you know what? That repair in place is not really just repair in place. It's alter a hell of a lot in place and build a bunch of new stuff. And that's a surprise to us. We thought this was a condition assessment meeting, which is primarily what it was. And the condition assessment was pretty darn good. So that's my surprise, our surprise or my surprise as to why, I mean, we got half this thing made sense and it was well documented. And this part is like thrown here at the end. I can tell you in a business meeting and private enterprise, if this was happening, we would just stop the meeting and say, go back and get that last half done and we'll get together and talk about it when you have your shit together. Then you can make a decision. You need to have a reasoned approach to what you're evaluating. You can't just dump it.
Okay, we're gonna pause this here for a second. Let's keep going to the next slide. Do you have any questions?
First of all, I want to apologize for some of these folks, the way they're talking to you. I think they're way out of line. You can, get a bunch of new information. You can ask questions. Eric asked us to be respectful of each other and of our guests. I'm not hearing that over there, and I'm just calling you on that. That's fine. That's fine. One of the questions I had was you talked about the outfall, 1 and 2, and you said 2 has a different, tighter, permit on it, but you use that. How should we look at outfall 1 versus 2 in kind of assessing the whole thing? I mean, there's some of these that are very strict compared to on 2 versus 1. How do these two work together and how the permits work together? I just don't understand that part.
Meets outfall 2 criteria. So the way that water flows through the plant, through the entire plant and then goes to the 2 different outfalls, it still meets the same process. It still follows the same process, and the outfall 2 has stringent requirements, and the process meets outfall 2. It automatically meets outfall 1 as well. It's the same water going through, but then splits if it makes sense.
Part of the outfall. Sorry.
Yeah, I've seen it. They're not that.
It's here the same basin, just 2 pipes leading the same.
Okay.
Yeah, so it's not.
So they're right next to each other.
So it's the water flows the same path, the same basin, and then just.
Equally, is it split equally?
No, the flow going out.
Oh, that's the average, yeah, daily flow. Gotcha. Okay.
Because it's the same, water will follow the same process. We wanted to make sure we meet the outfall 2 criteria and not just take into consideration.
Gotcha.
So for our evaluation, we use it.
Okay, thank you.
So how does that change the analysis? I guess I'm looking at it. I don't understand. What? Average daily flow. So you're gonna choose 0.6 versus 7.8?
Yeah, that's just the amount of flow, amount of water,
Right.
water going through. So the only 2 differences, sir, are the CVOD as well as the ammonia. So that would go through your aeration basins. That's where we want to make sure the aeration basin has the right capacity to meet your ammonia criteria. With the right amount of air into the aeration basin, right amount of oxygen.
So if you chose 1, how does that change the shit?
Not by that much. But again, because the plant currently has 2 outfalls, and they have to meet the outfall 2 requirements, we wanted to make sure that the entire process, whichever alternative you do select, meets that outfall 2.
And with the slide 58. We've already talked about this one. Mr. Smith, did you have any further questions on this?
Yes, I mean, you made the comment. 561, that you did not consider obtaining any TCEQ exception. Why is that, and what's the procedure to achieve that? So you mentioned here, chapter 217, on slide 61, you specifically said, we did not consider obtaining any TCEQ exceptions. Why was variances, okay? Why was that, and what's the potential impact of those variances?
Requires that start with flowing rate, here overflow rate. You could get a variance from TCEQ if you are exceeding that limit that TCEQ requires by certain versions. That has happened in lots of cases. However, if we start dissecting each process area, then you could potentially get variance under each of these alternatives to complicate the evaluation, because you could potentially get variance from any of these processes. Our assumption going into the evaluation, these apples to apples comparison, was to make sure that our assumption was we did not see EC2 areas in any of the processes. That is not to say that once you choose a certain alternative, you start going through the design process of an engineer, that engineer will not help you fine tune the design by after.
So how do you incorporate that potential in your initial evaluation to make sure you don't choose the wrong solution? I mean, I think the base case you have right now is the worst case scenario. No variances, okay? If I can avoid building 2 clarifiers by obtaining a variance, that's a pretty substantial impact on NPV.
Anything what the existing plans would not. So potentially, can you add peak flow storage? Like some of the additional basins that are there? Yeah, if we start dissecting each of these potential options, it could be 100 iterations that you would have to do under each of the alternatives to come to the solution. So we assume for now that there is no peak flow requirements, peak flow storage requirement, no variances, and we mimic the existing plan as is, what they currently have on the ground. All for.
Yeah, so this is on your experience. You see, use Brooklyn. The sewage system to prevent stormwater from entering. It's a stormwater entering the sewage system. Right? It's overflowing. It's not coming from homes. Right? It's coming from access to the sewage ports. I don't know the correct language. Have you seen communities take action to reduce that peak storage by correcting deficiencies in this?
Yes, a lot of cities go through line reduction policies, improvement in their collection system, where you are building pipes, lift stations, because if the pipe is full, the material is porous, it's hard to keep it. So yes, there are ways you could potentially minimize, but as I said, we are not even looking at that 5Q or 6Q that could potentially be seen at the plant. This is TCQ based requirements, regardless of what you are seeing. The base requirements is 4 times the average daily flows for the peak flow calculation. That's what CS2.
Question on.
Slide 60, was it?
I believe so.
Yes. And I briefly touched on it. It was, can you break it out so that the in situ, which in Latin is in place, is literally different than this one where you have addition of land in the top left and top right? Yes. And then this was more of a tactical question. I realize now that this is more for the SJRA, but the website, so I'll just put it out there, Ed and company, as a request. The website asserts that the existing wastewater infrastructure at the Woodlands is aging with certain treatment and conveyance components expected to reach the end of their useful life in the coming decade. Improvements must be made and actions must be taken. I take that part of that was what we saw here, based on what I hope in the next session we'll have some quantifiable data to be able to translate these assertions. The statement must be made. I was interpreting it as the base plan. One of these variations, one of the 4 to 6 variations, must be made. That's how I interpreted it.
Which website?
It was the SJRA, let's see, I have slash, it was that under sjra.net.
Okay.
And then wastewater treatment facility number 1. And there's a description of the project. And it makes reference to Carollo and property acquisition services, which I guess is the, in case you have eminent domain to purchase the private land lots on the top left and right. Yeah,
And
it was that one.
trustee authorized, just a quick update. Trustee authorized
SRA pursue land acquisition back in spring of 23. We put a land team together, started going through the process, put it on hold when we initiated this study. And so right now, land acquisition is on hold. We've not acquired any properties. Subject to what's going to come out of this study.
Okay, that's good to know. Just FYI on slide 60, 61, yeah. All of these do include the acquisition.
It shows the tracks, but that's it.
So it's showing you three blue line is the existing SGRA property lot.
Yes.
The blue line is potential property acquisition. However, the green line is a CPQ required 150-foot buffer that has to be there around treatment unit. Any treatment unit to be 150-foot buffer. So that's what we are showing. The existing plant needs the buffer and has the buffer. If you have to build additional clarifiers, you would potentially need that additional.
Mayor, would you mention that trapezoidal piece up at the very top?
I see the trapezoidal piece is the stormwater detention pond. And whenever you do any site improvement at any of the sites, you are required to do stormwater management of the sites by the county and the city. Township overlay. So we are assuming that you would need stormwater detention basin and under any of these alternatives because you do have some site improvements at this, because you're adding additional concrete.
What you're wanting is the blue modified, is existing structures that get repaired or modified versus.
So yeah, these light blue lines that are, each of those structures are the existing structures that will need modifications based on what Creevy and Stephen mentioned earlier today.
We're on our last few questions here. Mr. Thayer, you had a question on this one.
Yeah, I do. I've seen here a few minutes ago, you did a really good job of explaining a base case. And I like the way you explained it because then you can always say, I got a base case, I want to do some variants and I can tweak it and maybe get to a better economic decision for my constituents. However, when I look at this, which I think the whole idea behind the repair in place was to be a base case, I see something new here, like new stuff like a maintenance building, an administration building. How are those base cases? No, I'm on repair in place.
We wanted to keep it apples to apples. You can choose not to add those admin building or maintenance building under alternative one. Oh, and we can easily remove those 4 items that are common in these alternatives. That is, of course, your choice and whatever the recommendation is. But we wanted to keep that aligned and similar, as I said, apples to apples comparison. So you're not looking at the maintenance building at the existing equipment on information. So that's why that was happening. That was really the basis and reason why we had this core structure.
So the stormwater retention pond makes sense if that's going to be required. The other ones make no sense, and as they're an addition, they're an extra step beyond your base case that you were trying to define. I understand why you did it. I don't think it's a proper way to attack a base case.
The top left. Just to address Mr. Stevens' comment about the changes that I was recommending, it was really the addition, the top left dotted line corner, which is defined as potential property acquisition tier 2. It was just to have the property acquisitions moved from the base case, if you will. We use that language. Okay, thanks.
Do you have another question, Greg?
think we already asked that. I have a question on this one as well. Did you have a question?
Oh, I mean, my only question is, I think the more we learn or the more we hear, I think you misunderstood the original intent for the base case, alternative one, which was supposed to be a low cost, minimum effort, extend the life for 20 years. And it wasn't to be a apples and apples comparison with go build brand new stuff. Okay. It seems like you've added a lot to alternative one, which will drive the cost up and make it more closer in cost to alternatives 2 and 3 and 4, which wasn't the objective. The objective was to find the lowest cost possible solution that keeps our plant running for the next 20 years. And that's not what you're doing. And I don't need a new maintenance building to do that.
Before we wrap up.
Next steps, yes, sir.
So the next steps, as I mentioned, we are going through the cost process and for all 4 alternatives. We'll take some of your comments into consideration as well. We are working on our condition assessment report that ties the WJE report and the other assessment that we perform, Corolla performed of all asset types. We will get that draft report from SGRA as well. The next month's meeting, we will go through all these, some of these details on the process. As you mentioned, you want more information on how we got to the hydraulic capacity and process capacity for the existing plant. We'll go through that and also go through detailed evaluation of all 4.
So will we see a more detailed explanation of what the cost estimates are rather than just an NPV number?
Yes, that would be okay.
So just to break for each of the 4 NPD cases, are you going to provide your assumption? You're going to provide a project schedule, you're going to provide a cost schedule, and you're going to provide the discount rates, et cetera, the assumptions that you use to calculate your NPV. Can you give those to us before the meeting in a format that we can crunch our own spreadsheets to confirm?
Yeah, the request was to get the information ahead of time. That was a request from you at your meeting. They complied with that this time. I've asked for that same request going forward in the additional meetings. All right, I want to thank everybody for all your comments. I know y'all put a lot of thought into it, so I really appreciate listening to everything. With that, we are adjourned. Thank you.